Okay, everyone, let's get started. So today we will be discussing neural language models. So this whole week we will spend on neural language modeling. Today we will focus on the forward propagation phase, and on Wednesday we will talk about back propagation. And then for the weeks after that, we'll be talking about different composition functions that all generally use the forward and back prop phases that we'll learn this week. So this week is quite critical. And I'll also say that last week we talked about n-gram models. So this week we'll be departing from n-gram models. We noted several limitations with n-gram models. We'll be moving to models that you can't actually count and just get the parameters by normalizing like we saw in n-gram models. These are models that require training, and we'll talk more about that on Wednesday. So today I just want to kind of go through the computations that happen in order to get from a sequence of words to a probability distribution over the next word, given a neural network language model. Okay, so before we start, again, just a reminder of your deadline. So you have 2 this week. Your homework 0 is due on Friday, and your final group assignments are also due on Friday. Your project proposals are due on March 8th. I also added the deadline for the final project report, since many of you asked for this on Piazza. It'll be the last day of classes for the semester, May 17th. This is when your report and all of your code and any other associated deliverables are due. Also, I just posted on Piazza in the last hour about the extra credit assignment. So I've released the template that you should use if you want to earn extra credit. Basically, you will attend up to 3 talks that involve NLP that are happening at UMass this semester. You will summarize them using the template provided and submit them on Gradescope. And the exact amount of extra credit will be announced later once we have figured out what the weighting of the exam and things like that are. So this week, there are 2 opportunities for you to earn extra credit. Both of them are tomorrow. So there are 2 NLP talks that are happening. The first one by Sadia Gabriel is probably by far the more accessible of the 2, especially given how much we have covered to date in this class, which is very little. So this talk will focus on some of the social and ethical implications of large language models and other NLP technology when they're being deployed in real-world use cases. So there will be some technical components that you won't understand. You'll note on the extra credit form that it asks you specifically, were there things that you didn't understand? And these are things that you can read about later or just focus on, because we'll probably cover many of those things in this class. Note that this talk is 4 to 5 p.m. in the CS building in CS 151, so it is an in-person talk. You're all highly encouraged to attend. The other talk that is happening is earlier in the day, 11:30 to 12:30, and it's a remote talk. It's on Zoom. The Zoom link is posted in Piazza. This one is on decoding algorithms for language models. It is more technical and covers things that we haven't yet discussed in this class. So I would encourage you to attend this one if you already have some prior NLP background. Otherwise, it might be a little over your head. You'll find that as the semester goes on, you'll be able to understand more and more of the talks that we're having here. So again, there's an overleaf template, so all of these extra credits must be submitted using this template, and it's available on the website. All right, any questions about this or, yeah?
So is there going to be like a document that outlines the requirements for a final project?
Yeah, so the question is about the requirements for the final project. Just like your project proposal and the extra credit, there will be an overleaf template that has all of the the required sections that you need to complete and the page length and things like that. So yes, that will be released probably in the next month or so. Other questions? Oh, that's right. Sorry, I forgot about that. Yes, so I will also share on Piazza some sample project reports. So you can I'll probably share like some of the good ones that we've collected over the years, so you have a good idea of like what goes into a successful project report that was graded well. All right, so let's get started with the actual topic of the day. And again, just to review the concept of language modeling, the goal here was to compute the probability of a sentence or some piece of text. We talked about two equivalent formulations of this. One, you can compute the probability, the joint probability of the sentence, or you can compute the conditional probability of the next word given all of the previous words, which we called the prefix. So by the chain rule, we can recover the joint probability from the product of these conditional probabilities. And in this class, we will be focusing on models that compute that conditional probability of Wn given all of the words before Wn in the text. Oh, I see there's a question. Are talks on Zoom going to be recorded for future use? Yeah, they will be recorded. We're not sure yet about the details, but they probably will be recorded on Zoom and you will be able to access them. I assume this is for the extra credit. I think this is also true of the in-person talks, but I'm not actually sure about the accessibility of those. So for tomorrow's talk at 4, if you want to attend, you should come in person. All right, so let's just review the n-gram models that we were talking about last class. So given this prefix, students open there, I might be interested in the conditional probability of the next word being books or something like that, right? So I can model this conditional probability by counting up how many times students opened their books occurred and then normalizing that by the count of how many times students opened their occurred, right? And we talked about things like bigram models in which I might ignore parts of this prefix because it's too long. I'll just chop it off to the previous word. In a trigram model, I would consider the last 2 words and so on. So let's take an overview of the issues with these n-gram models to kind of motivate where we're going now. The first is something we talked about towards the end of the last class. So what happens if students open their W, whatever this W is, never occurred in your training data? Then you have a 0 probability of this word occurring, even though it might be a plausible word, right? I might be interested in students open their laptops, but laptops never occurred in my training data set. So this just has a 0 probability, which is clearly bad because that's a valid and acceptable construction. So we talked about smoothing as one way to deal with this issue, where we might steal some probability from words that actually were observed in the training data after this prefix. So for example, if I observed students open their books and students open their notebooks, I could steal some of the probability away from those observed words and add it to my unobserved word, laptops. But this is kind of a hacky solution, right? Because as far as the method that I described, all unobserved words get the same probability mass. So laptops might get the same probability added to it as like zebras, right? Which is clearly not what you want. Laptops is way more acceptable in this context than zebras. So overall, the sparsity is a big concern. Even if you have a very, very large training data set, if the order of your n-gram model, so the number of words in the prefix that you're considering is high, you will encounter sparsity where you just can't observe all acceptable sequences of that length in any size training data. So yeah, we talked about smoothing. There's other problems, right? So what about the storage issue of n-gram models? So you might have heard a lot about large language models in the context of neural networks, but n-gram models can get much larger than even the largest language models that we have today that are based on neural networks. That's because if you imagine that count table that I was keeping track of with the bigram model, right? I had all the possible prefixes as rows and all the possible next words as columns. So with a bigram model, the size of that table is the size of the vocabulary. Let's call that V. It's V squared, right? Because I have all the possible words that can occur as prefix on one in the rows, and then all the possible words that can occur next as columns. What happens if this is a trigram model, right? Now, the rows of this table are actually all two-word combinations that I have in my, that I can form, right? So here, now, the number of rows that I have is already v squared, and then I have another, the column dimension, which is this v, right? So now I'm keeping track of v cubed different counts. You can see that as I extend the order of my n-gram model, I'm exponentially growing the size of this table, which is why it's additionally not feasible to have high order n-gram models, especially on very large vocab data sets. So this is a big problem in addition to the sparsity, right? It quickly becomes intractable to even deal with these huge count tables. All right, so finally, another issue, even if you set aside all of these other ones, is that in such a count table, you're treating all words and all prefixes independently of all other words and prefixes, which doesn't make sense, right? So if I have students open there, and this is the prefix I'm interested in, this is very similar to scholars open there, or undergraduates open there, or students turn the pages of there, right? All of these are semantically very similar to each other. If I observe a count for undergraduates open their word, intuitively you might want that to influence your conditional distribution after observing this prefix students open there. But this does not happen in an n-gram model, right? All of these are treated as separate prefixes in the table. There's no sharing going on between these semantically similar entries. So this is why you have that sparsity problem, right? Because everything is treated independently of the other entries in your table, and this is not ideal at all. This also contributes to the big storage costs. All right, any questions so far? Okay, so let's take a look at why these entries in the table are treated independently and kind of build our way up to more distributed representations of words and prefixes rather than these kinds of completely independent representations. So in an n-gram model, the way that we've defined it, it relies heavily on what's known as a bag of words assumption. So in a bag of words, you represent each item in your vocabulary as a one-hot vector. So this is a vector that's of size, the dimensionality of this vector is the size of the vocabulary. And all of the entries of this vector are 0, except for one dimension which corresponds to the particular word that you're at. And that dimension is set to 1. So you have, for example, here the word movie. If I have a 6 word type vocabulary here, I have this vector where it's 0 in every place except 1, which corresponds to the 5th word in the vocabulary, movie, right? If I have this word film, right? Film is a synonym of movie, right? So ideally, movie and film would have a similar representation. However, in an n-gram model and in any bag of words model, film has a completely different one-hot vector where it's 0 in the dimension that corresponds to movie, and it's 1 in the dimension that corresponds to film. So what does this mean in practice? It means that every single word type in your vocabulary is equally similar and dissimilar from all other words in the vocabulary, right? So if you see like these two words, their dot product, if you use the dot product to measure the similarity of these two vectors, is 0. And in fact, these vectors are orthogonal, right? And this is true of every single word vector in our vocabulary. So this means that there can be no sharing of information going on between these different word types. They're all treated completely independently of each other. Okay, so now we're going to move to a setting in which the representations of the words are no longer one-hot vectors. So if you imagine, instead of having this 6-dimensional vector, maybe instead of that, I had a 2-dimensional vector where the values were not binary 0 or 1, but they're real value. They could be like 0.34 or 0.55 or -7, right? So now you have a way of making two words that are kind of similar to each other have similar vectors, have a dot product that is, reasonably high, and showing that these two words are similar, which is not possible with this representation of words and prefixes. Okay, so the ideal case here to avoid some of these issues we've talked about with n-gram models of sparsity and space and so on is that we want a word level or phrase level or text level representation where words, phrases, and sentences that are semantically similar, so they mean similar things, are also, they have similar vector representations, okay? So that's our goal. That's essentially the goal of any more complicated language model compared to an n-gram model, is that you actually want a more powerful representation space. Okay, so with a neural network language model, we're trying to accomplish these goals. And at the highest level, instead of the n-gram method where we just simply count the occurrences of these prefixes and words in our training data set, here we will pass our prefix into a neural language model, and the model will produce a distribution of the next word conditioned on this prefix. And so this is a machine learning model, the red box here in the middle. This is a model that has parameters that are trained using an error signal to guide the updating of the parameters. And so this is what we're going to be talking about for this lecture and the next one on Wednesday. So in this lecture, we will specifically focus on what's called the forward pass or forward propagation of these neural language models. So this is, how do we go from a text like this, students open there, to the output prediction of books given this prefix. And this is mainly just following a set of equations that are defined by the architecture of this neural network. We will not talk today about how to adjust the parameters of this network to make better predictions of the next word. That is a process called backpropagation, which we will talk about on Wednesday. So just before I continue, how many of you are familiar with forward propagation and backpropagation? Okay, so it looks like more than half of you. But in any case, this will be a review, and also for many of you, and also will serve to introduce some of the language modeling architectures that we'll be discussing in this class. So hopefully it won't be a complete waste. All right, so we will start with how do we represent words in these kinds of language models. And later on in this semester, we will talk about other units of text that we might want to start with. Because, in the first class, we talked about characters and subwords as being even below words, right? So we might want to represent those things instead of words. But for now, we'll just look at words as the basic building blocks of a piece of text. So instead of representing words with these one-hot vectors, which are 0 everywhere except for one dimension, we're now going to replace them with some low-dimensional, real-valued vectors that are called embeddings. So if you hear this word embedding, it is referring to a low-dimensional, dense vector, like something like this. So the word king, if we had a 4-dimensional embedding for it, it might look something like this, where we have these real values in each dimension instead of just 0 or 1. Yeah.
So my question is, sometimes words have different meanings, and those different meanings might be something we want to be semantically similar to some other word meaning, but it's not to another word that is semantically similar to that word. So how do you deal with that?
Yeah, that's a great question. So some words have different senses, for example, right? The word bank, it could be like a financial bank, or it could be the bank of a river, or it could be a verb. So it has many different meanings. In these kinds of models, if we were using a word level model, we might represent the word bank with the same vector for every sense, which, as you say, is limiting because it kind of conflates 3 different usages of the word into one representation. So there are many ways to deal with this. We'll talk later on about the effect of context on word meaning. So we can start with a vector for bank that is static and the same for each sense, but then our model should be able to recognize the context that surrounds that word and update its vector to kind of be more in line with one of those three senses, whichever one is most appropriate for that context. So we'll talk at length about this. The other way you could handle this is use a different type of representation. So instead of words, which might be too coarse, you could go to the character or byte level, in which case you have much smaller vocabulary, but you can build up the representation of words using context more heavily. Okay, other questions? All right, so let's start here. So let's assume that for now we have randomly assigned every single word type in our vocabulary to a randomly generated vector like that looks like this. So all these numbers are random to start with. That's how all language models, neural language models work. Their parameters are initialized at random to begin with, then they're slowly updated as you see more and more training data. So let's assume that we have these word embeddings. They're randomly initialized. Now, the goal of our neural language model is to compose the words that make up the prefix into a single vector that represents the meaning of that prefix and that can be used to predict the next word. So if we have students open there, like just continuing with this example, we are going to use a neural network composition function to take the three embeddings associated with these tokens, students opened there, and kind of synthesize them into a single vector, this one over here, that contains the semantic meaning of that prefix. Then we're going to use this composed vector to predict the next word of this prefix, so hopefully it's books. So this is the high-level workflow of a neural language model. We first take the prefix, we get a vector that represents the meaning of that prefix, and then we use that vector to predict the next, the distribution over the next word. So you can, again, yeah, go ahead.
I was curious, what's the difference between embedding and encoding?
Embedding and encoding?
Yeah.
So with embedding, actually these words can be used kind of synonymously, but people generally use embedding to refer to the word vectors here. Encoding you can also think of as a process for like embedding a word or sentence into a vector. It is used more or less interchangeably in papers. Yeah. Okay, so just wanted to add a little bit more contrast to an n-gram model. So in an n-gram model, we never did any of this, right? We directly got the conditional probability from counting and dividing. Here, it's much more complicated and time-consuming to get to that point. All right, so let us take a look at, in more detail, how we predict books. Like, what does that even mean? So before we start with the composition process of how do we get this vector out of students open there, we'll take a look at the final stage here, the output layer. So how do we go from this vector to predicting books? Once we understand that, then we can talk about this part, or how we compose all of these different embeddings into a single embedding of the prefix. Okay, so for those of you who have some experience with neural networks, we're going to use what's called a softmax layer. This is probably familiar to many of you. It's very useful for any sort of classification problem. And if you're familiar with using neural networks for classification, a neural language model is just a classifier. It is a classifier that takes some input and classifies the next word into one of V different labels, right? Where V is the size of the vocabulary. So it's a very large output space where you could potentially have like 100,000 or 200,000 next words. But at its core, it behaves the same as any other classifier. You just have a very large label space. Okay, so our goal is to get a probability distribution over the V word types in our vocabulary, right? We saw this thing before. These are all the word types from A to Z, and we might want a distribution that assigns high probability to books and laptops and low probability to something like zoo. So this is our goal. This is what we want to get as output, and we want to get this from our low-dimensional vector that corresponds to the meaning of the prefix. So this distribution is the probability of the next word given this vector for students opened there. That's what we want to compute. All right, so let's look at this through a simple example. Let's assume we have a vocabulary that has 4 word types in it. We have books, houses, lamps, and stamps. This is just for the output. Very simple vocabulary. So what we want is a distribution over these 4 word types given this prefix students open there. So we might want something like this, where the probability of books is 60%. This is just an example. Obviously, here we might want 100% probability on books. But you want a well-formed probability distribution over these 4 word types. So let's just work our way through some of these calculations. So let's say this vector representing our prefix, this is a 3-dimensional vector, just for the sake of example. It might look like this, minus 2.3, 0.9, and 5.4. So this is a vector that represents the meaning of our prefix. We have computed this vector using our neural network composition function, which takes as input the 3 word embeddings corresponding to students opened there. Yes?
Is the dimensionality of the prefix vector necessarily the same length as the prefix? So here, students open there is a 3-word prefix.
I see. That's a good question. So this is a 3-dimensional vector. Our prefix was 3 words long. This is not necessarily the same. So the dimensionality of the prefix vector is a fixed value that is set by the designer of the neural network. So I could have set this to 100 or 500. It is the same regardless of the length of the prefix. So I might have a 3-word prefix, I might have a 10,000 word long prefix. I still want to obtain, in this case, a 3-dimensional vector that represents the prefix. So that's called a hyperparameter, the dimensionality of the prefix. Do you have a question? Yeah, so this is a hyperparameter. It's the hidden state dimensionality of the model. I see a question here. How can we show the semantics of a word as a vector? So I'm not sure I understand the question, but we will talk more about how we can kind of probe these vectors to obtain some insights on the type of knowledge that they contain. But that'll be much later on in the semester. So there are ways to do this, but again, I'm not sure I understand. Okay, so in this example, we have a 3-dimensional prefix vector. And in any sort of neural network, we're going to have parameters of the model in weight matrices. So this is a weight matrix. These numbers are all just completely random for now. Each element of this weight matrix is a parameter of the model. Just like the word embeddings, over here, these word embeddings that are randomly initialized are also parameters of our model. So a parameter of our model is something that we want to update through the backpropagation phase, which will hopefully become more clear on Wednesday. So now we'll just talk about the math that we use to get from this prefix vector to that 4-dimensional probability distribution over the word types in our vocabulary. So in other words, we need a way to project this 3-dimensional prefix vector to a 4-dimensional vector that we can then use to compute this probability distribution. And we can do this with a simple matrix vector product, right? You'll note that this matrix W is a 4x3 matrix. So if we take the product WX, we will get as output a 4-dimensional vector, right? So this, if you're having trouble with it, you should review some basic matrix arithmetic, matrix vector products, and so on. Those are kind of the bread and butter of any sort of neural network. Okay, so let's look at some intuitive, intuition behind these dimensions of the prefix vector. So here we have a three-dimensional prefix vector. It can be useful to consider each of these as kind of a feature of the prefix. So perhaps the first dimension encodes something about the part of speech, whether or not it's a noun or a verb. The second dimension might encode something about you know, like how many words were in the prefix or something. You know, all these linguistic properties that could be important for predicting the next word, they could be encoded in the prefix vector somehow. The catch is we don't have any way of interpreting these numbers, right? I can't just look at this and say, oh, this is a minus 2.3 nouns, or like that doesn't make sense, right? So we don't really know what this means, but it's useful to think about it in terms of these are features of the prefix. They contain some information on different aspects of this phrase students opened there. So if we look at it that way, then we can kind of also apply this intuition to our weight matrix W. So you'll note that W contains 4 rows, right? Each row of W you can interpret as corresponding to feature weights of one of the word types in the vocabulary. So we can assume that this first row here corresponds to the feature weights for books. So you can see that this first dimension of the prefix vector is kind of important for books. The second dimension may not be so important, and so on. You can look at lamps. You know, in this random example, it has a high weight on the first element, the first dimension of this vector, and lower weights for the other ones. So you can kind of view it as how important is a particular feature of the prefix vector for the prediction of the next word. Now, I just want to again emphasize the caution that you cannot easily interpret these features, right? The second dimension of X here does not really correspond to any linguistic property. In practice, it's actually groups of these different dimensions that do have some predictive ability, property of some linguistic feature, but it takes some effort to figure out what each dimension corresponds to. But I'm just framing it in this way so that it's helpful for you to understand the role of the different dimensions in the prefix vector and also the role of the rows in the weight matrix. Yeah?
So do these numbers have a specific range?
Do the numbers have a specific range? This depends a lot on the structure of your neural network and some of the hyperparameters under, you know, like what activation functions you use. In general, the hidden states of the model may have a specific range based on the choice of activation function, which we'll talk about later. The parameters in these networks rarely have a specified range, although you might regularize the weight matrix, so that means you might want to have some sort of penalty when the values get too large. This used to be quite common, but nowadays I think people don't really use it anymore. It's not needed. Other questions? Yes.
Having more number of dimensions always beneficial?
Is having more, like a higher number of dimensions always beneficial? So right now we have 3, right? And that's pretty low dimensional space. Maybe we can't learn that many complex properties of the prefix. What if I extended this to 500 or 1,000 or 10,000? Is it always better to have more? The answer really depends on the data set that you're training the model on. So if I have a very small data set, then if I had 1,000 dimensional prefix vector here, I'm very likely to overfit the training set, which means I do an excellent job of predicting the next word on my small training set. But when I go to apply this model to the test set, it just completely breaks because all it's done is memorize the next words that occur in the training data set. It never had to generalize to actually learn anything about the language. So this is a very common phenomenon, and it basically means that you have to choose the dimensionality of your model based on, you know, the size of the data that you have. There's no clear-cut way to do this. Normally, people just pick values that other people have used in the past successfully, and it's very expensive to search through all possible values because every time you change it, you have to retrain a whole new model and then compute its perplexity, right? We talked about perplexity last class, see if it's lower on the test set than this other model. So yeah, it's kind of like an art, is picking the right hyperparameter values. And in general, people try to avoid this by just using some standard values. All right, yes?
How is your weight matrix assigned? How do you know which one's the weight matrix?
So how is the weight matrix assigned? So we'll talk throughout the semester about different neural network architectures. Each of them have a different series of computations. This is just one fundamental block in any of those neural networks. So this weight matrix may be assigned to participate in the computations at layer 13 of some model or something like this. We start by initializing all of these numbers randomly. So before we see any text at all, these numbers are completely random. And then as we see more and more text and we start predicting the next word, we will update these numbers so that they give you a better prediction of what the next word is. Hopefully it'll become more clear as we go on and talk about the actual units of the network as a whole. Yes? Yes, so the question is the dimension of this weight matrix is V by the dimension of the prefix vector, right? So we have V rows of this weight matrix here, and I want to emphasize that this particular matrix, W, only occurs at the final layer of the model when you're predicting the actual probability distribution. So all of the other W's in the model are going to be smaller. They're going to be denser, maybe like, you know, 1,000 by 1,000 or something like that. This particular matrix is always the biggest one in the neural language model because one of its dimensions is directly tied to the size of the vocabulary. Now, that is not the case if you're using like a character level language model, right? Because there you have a very small number of characters for each language. So this matrix might actually be much smaller than, but for a word level language model, yes, this is proportional to the size of the vocabulary.
Are there other factors to consider besides like data set and vocab size when picking the embedding dimension?
So what other factors might you consider when picking the dimensionality of the prefix vector other than just size of the data set? One thing which is more practically a concern to most people is how much computational resources do you have, right? So in general, it's more useful to increase the number of layers of your model rather than make the dimensionality at any one layer larger. But there's always a trade-off, right? You can't make like 100 three-dimensional layers is probably not going to be as good as you know, like 500 dimensional vectors or something. So as I said, there's no clear way to do this, but generally you want to max out the memory on your GPUs. So that's another thing that is probably the most common consideration. All right, let's move on. Oh, we have questions. ChatGPT is also a neural language model. Can you estimate the dimensions of a word in ChatGPT? ChatGPT is based on GPT-3, so you can go to the GPT-3 paper and look at the dimensionality of the model. They've posted it. I'm not actually sure what it is. I think it actually changes depending on the size of the model. The 175 billion parameter one, I would imagine, uses several thousands. The dimensionality of the prefix is several thousands. Once training completes doesn't mean that every row of the weight matrix can be considered as the vector of that word. That's not true. So this weight matrix is used to get the final probability distribution of the next word. The row vectors here are not the meaning of the word. They're not the embeddings of the word. So that's a different part of the model. That's a different set of parameters. So you can consider this row vector as it is also a representation of the word, but it's more like the feature weights that are most important for predicting the next word for that, if that word is the next word. So we'll cover this later on when we get to the full transformer language model. All right, so let's move on. I have this weight matrix, and I have this vector x that represents my prefix. So now if I compute this matrix vector product wx, I get a 4-dimensional vector. So I'm getting closer to my ideal target, which is a probability distribution over the 4 words in my vocabulary. Now I have a 4-dimensional vector, but obviously this is not any sort of probability distribution, right? So if you're confused about how we computed this, it's just the dot product of each row of this weight matrix with our prefix vector here. So you note that each row of the weight matrix is a 3-dimensional vector that we talked about intuitively as corresponding to feature weights. And each dimension of x corresponds to some sort of features. So if I wanted to compute this first element of the matrix vector product wx, I take my feature weights that are in the first row of w, and I multiply them element-wise with the features that are in x, right? So 1.2 times minus 2.3 plus minus 0.3 times 0.9, and so on, right? I just do this simple process, and I get 1.8. And all of the other values in this vector are computed similarly, right? This one is just using the second row of these this weight matrix rather than the first. So again, if this is unfamiliar to you, you should review your linear algebra and just make sure you know what all these, how these matrix vector products and dot products of vectors and so on work. All right, so we have a 4-dimensional vector now, but we're not done, right? This is not a probability distribution over the next word. So to convert this vector into a probability distribution, we'll use what's called the Softmax function, which again is probably quite familiar to many of you who have experience with these kinds of models. So the Softmax function is very simple. It first exponentiates each element of the vector that you're applying it to. So you can see this e to the x here. And then it just normalizes by the sum of all of the values in that exponentiated vector. So just looking at this equation here, x is a vector, x sub j is a dimension of x. So what we're doing here is first we exponentiate all of these values of wx. So we take e to the 1.8, e to the minus 1.9, and so on. And then we just divide by the sum of all of those values in the resulting vector. So if we apply the softmax function to this vector here, we get something like this: 0.24, 0.006, 0.73, 0.02. And we are interpreting, remember, each dimension of this vector as corresponding to one of the word types in our vocabulary. So now we can interpret this as the probability of books given students opened there is 24%. Unfortunately, it looks like the probability of lamps given students opened there is quite high. But remember, this is just a completely random example. Ideally, when we start training this model, once we find that the probability of lamps is 73%, the probability of the correct next word, books, is 24%, we can compute an error term, right? We can say, oh, you should have assigned actually 0 probability to lamps and 100% probability to books. So you can compute an error and then we're going to use that error to adjust all of the parameters of this model such that next time we see this students open there, we will have a much higher probability for books. That's the general idea. Okay, so question for all of you, if you're familiar with this function or not, is why are we using this particular function? Like, what makes the softmax function useful in this regard? What are some properties that are, yeah? So it makes the values of all the elements in the resulting vector between 0 and 1, which is obviously good. Also, the sum of all of the elements in that vector is 1, right? So again, these are properties of a well-formed probability distribution. But, you know, there are many other functions that could result in the same properties, right? Yes, so that is a key element, which probably will become more clear, and I see also Jay in the YouTube chat said the same thing. This is a differentiable function. So that means we can take derivatives of this function. If we have an error term, we can differentiate through the softmax function and figure out exactly how to update our parameters to do a better job the next time. So this is something we'll talk about at length on Wednesday. Any other ideas?
Because it's an exponential, it separates out the probability.
Yeah, that's right. So as I mentioned, there are many functions that you can use for this. One advantage of the softmax function is that we are exponentiating each element in this vector. So otherwise, small differences might be amplified using this function, which could make it easier for the model to learn like it's doing a good job or a bad job, rather than having some troubles with the optimization. Another reason is when we pair the softmax function with the cross entropy loss, which is the very common formulation for any classification task, the derivative of when you differentiate through the softmax is very, very simple and efficient to compute. We may talk about that if we have time on Wednesday, but that's just another reason, which is probably irrelevant nowadays, given that these libraries will just compute all the gradients for you. All right, so we will use this function over and over and over again in the semester, not just for getting a final probability distribution over the output, but also in the internal layers of models like the transformer. So you should study this carefully and make sure that you understand why we're using it and how it works. All right, so just to sum up, we are given a d-dimensional vector of the prefix that in this part of the lecture, and we do the following two steps to predict the distribution over the next word of the prefix. So what we do first is we project this prefix vector to a v-dimensional vector, right? And how did we do this? We took our W matrix, which was of size v by d, where d is the dimensionality of the prefix vector. We computed this matrix vector product wx. So we went from a 3-dimensional vector to a 4-dimensional vector through this projection, right? This is just a linear projection. Once we did this, we applied the softmax function to the result in order to get a probability distribution over the v different word types in our vocabulary, right? So this is the operation of the softmax layer in a neural language model. Okay, so assuming that we all are on the same page and we understood how we get to be able to predicting books given this prefix vector, now we can return to this original problem of how do we get the prefix vector in the first place, right? I've just ignored that and assumed that we went through this process already. Now let's come back to it and see how we get there. So this is the process of composition. You have a variable length sequence, right? Like students open there is a 3-word sequence. I could have students turn the pages of there, which is, I guess, like a 5 or 6-word sequence. In any case, I want to be able to get a single fixed dimensional vector out of these prefixes. So the way I will do this is through what's called a composition function. So the input is a variable length sequence of word embeddings that correspond to the tokens of the prefix. the output is a single vector. So the simplest possible way to do this is to use an element-wise function. So if I have these 3 word embeddings for students opened there, I can do element-wise addition. I can just add the first dimension of students with the first dimension of open with the first dimension of there, and I get some value, right? I can do the same for each of the second dimensions and each of the third dimensions, and the result is a 3-dimensional vector that is a function of all of the 3 word embeddings, right? So what is an issue with doing this?
It's not actually encoding any positional state with respect to the words.
That's right. So if I use element-wise addition to get this prefix vector, the vector for students opened there will be the same as a vector for their students opened or opened students there or any combination of these words, right? So the order is not encoded. And of course, in language, order is extremely important for meaning. You have a question? No. Okay. Okay, so another thing we could do is concatenation. So we can concatenate the previous words of the prefix together and then use that as our representation. This has some limitations. We can address some of those limitations by moving to more complicated neural networks like convolutional networks or recurrent networks. These also have limitations of their own, which brings us to our focus model of the semester, which is a transformer. This is the one that is used by ChatGPT and so on. It also has its own problems that will be solved probably by next year's class, or and I'll have to update all these slides. But so far, the transformer is going strong. So it was introduced in 2017, and then it has been the architecture of choice to scale up all of these huge language models for now. All right, so we'll take a look at the most simple one of these composition functions that also takes into account order information. So obviously just adding all the vectors together is not a satisfying composition function. So let's look at something more complicated. So the problem with concatenating these word embeddings together is that it does not work if you have variable length sequences. So if I have a 3-word prefix, and let's say I have 3-dimensional word embeddings, if I concatenate the 3 embeddings together, I will get a 9-dimensional vector, right? If I have a 5-word prefix, now I'm going to get a 15-dimensional vector if I concatenate all of these word embeddings together. And so the whole process that I just talked about, where we get from a prefix vector to a distribution over the vocabulary, this requires that we have a fixed dimensionality for the prefix vector, right? So I can't be having 3, 5, 15, 39, like I can't be having all of these different dimensionalities of vectors if I'm going to actually go through this process with the softmax layer. So what happens in a fixed window neural language model is essentially we combine the insight of the Markov assumption, which we talked about with an n-gram model, with this kind of word embedding based framework that we've been discussing. So if I had a prefix that was, as the proctor started the clock, the students opened there, right? If I wanted to concatenate these word embeddings together as my composition function, I need a fixed dimensionality for the output of this. So what I can do is just chop off some of this prefix, just like I did in an n-gram model, and I can consider only the last k words and concatenate them together. So in this case, I will always have a 12-dimensional vector, regardless of the prefix, because I'll just ignore all of the words that came before that. Yeah?
As an open network, couldn't you also just have some maximum prefix length and then add
Yeah, so the suggestion here is instead of chopping off these words, why don't I have some very large max prefix length limit and then just add some padding tokens or something so that we're able to represent all of these words. You can certainly do that, but it's highly inefficient. It really depends on, like the sequence length. You want to be able to predict the next word from a 2-word prefix and a 2,000-word prefix with the same model. And if you do the approach you mentioned, In the former case, you'll have a huge amount of padding tokens, which will waste compute. Also, there are probably issues with sparsity there, depending on the architecture of the network that goes on top of this composition. So you could do it, but not advisable. Yeah.
You mentioned long-distance dependencies as a problem with n-gram models. How does this address that difference?
So that's a good question. So the question is, how does this address long-distance dependencies, which were a failing of n-gram models? The answer is it does not. This has the same problems with long-distance dependencies as an n-gram model. We'll look in a few minutes at a model that does not have these issues with long-term dependency. All right, so let's say that we're using this Markov assumption. What we'll do is we'll take the previous 4 words, we will take their embeddings, we'll concatenate them together. So now we've gone, okay, let's say these word embeddings, just in this example, they're each 4 dimensions. The dimensionality is 4. So if I concatenate these 4 words together, I have a 16-dimensional vector, right? So now what tends to happen in these kinds of neural language models is that we have what's called a hidden layer. So we take this representation and we pass it through a hidden layer where we apply a matrix vector product. So this is similar to what we discussed earlier with the softmax layer. Here we have this weight matrix W sub 1. And you can see that this vector here, that is the output of the hidden layer, is a 12-dimensional vector. So we projected this 16-dimensional input vector down to a 12-dimensional hidden vector. So what is the size of this weight matrix W sub 1? How do we accomplish this projection? What does the dimensions of this vector need to be? 12 by 16, yes. So this is a 12 by 16 weight matrix, and X here is this 16-dimensional vector. So when we compute this matrix vector product, we get a 12-dimensional output vector. Now you'll notice that there's this F here. So in the softmax layer, this F is just the softmax function. In the internal layers of these models, we don't generally use a softmax. We use other activation functions. And the reason for having this F is that usually it's a nonlinear function. So we want to be able to model nonlinear relationships or complex relationships between the input and the output. And we can't effectively do this with just a linear model. Like if I wanted to stack a bunch of layers of this kind of WX matrix vector product with different weight matrices, I wouldn't actually be able to do this if I didn't have this nonlinear function, because I can just collapse all of those layers into a single layer by just looking at the matrix products here. So the nonlinearity is important if we want to add more depth. The most common nonlinearity that we see today is the rectified linear unit, or ReLU as it's more commonly known as. This is a very, very simple function. So it's basically just y equals x, except if it's negative, in which case it's y equals 0. So this is one of the simplest nonlinear functions that you can have. The one potential issue that you might see is that this is such a simple nonlinear function. How can it be used to model very, very complex nonlinear relationships? And just for the sake of time, the answer is that this function is applied element-wise and at different layers of the network. So even though it itself is very simple, when it's used for like thousands of units at different layers of the network, it is capable of representing extremely complex nonlinear relationships. All right, so we got this hidden layer, this hidden vector here, this 12-dimensional vector. And now we are going to use our softmax layer to project this into a vector of the size of the vocabulary that is also a valid probability distribution, right? Using the method that we just learned. Okay, I see a question. Why can't we stack the word vectors instead of concatenating them? Not sure what you mean by stack, so perhaps you can ask on Piazza or something like that. But as you can see, this is a very, very simple neural language model, right? We took the softmax layer and we essentially just added this concatenation function on top, followed by a single hidden layer and then the softmax layer. If you did your reading, how many of you did the reading? Okay, it's more than last year. You will notice that this is the actual architecture of the model that was introduced by Bengio in 2003. It is the very first neural language model that was ever constructed, was essentially this. And it has been, you know, it is just the basic core of the models like ChatGPT that we see today. All right, yeah.
For the purposes of that question, I believe that they mean is instead of 6 by 1 vector, each one is 4 by 4 vector.
Oh, I see. And then you could use some sort of convolution or something. Yeah, you could do that, but that's a different model. All right, so how does this compare, going back to your point, to a normal n-gram model? Because it clearly has the same limitations of any n-gram model, right? You're only concatenating the last n words together in the prefix and ignoring all of the rest. So one issue is that, you know, in terms of problems, we're still using a fixed window. We still can't handle long-range dependencies. There are some improvements. We have gotten rid of, in general, our sparsity problem, right? So now if I have a prefix students open there and I have undergraduates open there, those are both being handled by the same function. There's no longer any one-hot vectors representing the words. And so I am sharing information between these two prefixes. So this is very good. The model size is no longer exponential in the size of the vocabulary, right? I have a model that's actually like linear in the size of the vocabulary. If I wanted to add more items to my vocabulary, I simply need to add more word vectors for each word type there. But I don't need to consider all combinations of 4-word phrases, right? That v to the 4th is no longer here, because note that for any 4-word prefix, I'm just breaking it up into the individual word vectors and then applying this function. So the learned function is taking care of the composition. I don't need to explicitly count all of these unique 4-word phrases. Yeah.
What is the drawback of like making R that's just like a paragraph for like 30 words?
You mean the window size?
Window size, yeah. Just make it
So that comes up for this last limitation here. So in this current model, if the word the occurs at the first position of the prefix, I'm handling it separately than if the word the occurred at the second position or at the third position or at the fourth position. If you think about this matrix vector product W1, a completely different set of weights is used during the multiplication depending on where that word is in the prefix, right? So essentially I'm forcing the model to learn how to handle the word the, but at different positions of the prefix, which is a kind of a waste, because we want the model to know how to handle the word the in general, not at the 34th position of the prefix, right? So in some sense, this is overkill, and we would like our parameters to be equally useful for every position of the prefix. Other questions? All right, so we have about 12 minutes left. Let's see if we can get to a different model. So now we'll talk about recurrent neural networks, which kind of fix some of these problems that we've just been discussing with the limited window size and also the lack of sharing weights between different positions of the prefix. So we'll take our same prefix, the students opened there, but instead of doing this concatenation followed by a hidden layer operation, we're going to operate over this prefix left to right, just like how humans read a text is, or at least in English, from left to right. So we're going to process one word at a time. So in a recurrent neural network, we basically will start with some initial hidden state. So this hidden state is eventually going to represent the meaning of this full 4-word prefix. But of course, before we've seen any words, we don't really have any knowledge of the prefix. So we'll start with some random vector here, which is called the initial hidden state. And then we'll update it word by word, left to right. So here we observe the word the first word of the prefix, and we will apply a projection, linear projection, using this W sub E matrix to the word embedding of the. Then we'll also apply a projection on the previous hidden state, which we'll denote by this matrix W sub H. And if you look at this equation here, we're taking two matrix vector products, W sub H times the previous hidden state, HT minus 1. So in a recurrent neural network, because you're going left to right, you have the notion of time steps, right? You have a specific time, or you can view it as position, where you are doing a computation. And so this first term is basically incorporating the previous hidden state, so all of the knowledge you had about the previous words in this prefix, into the current word that you're seeing, which is represented by here. So you add these two matrix vector products together, then you apply a nonlinear function like what we discussed in the previous model. And this is our recurrent neural network update equation. So I've done this for the first word, the. Now I have a new hidden state. You can see this is H sub 1. So now it's called a recurrent neural network because I can use the exact same equation to process the second word. So I'm going to step forward to the word students at the second time step. And you can see that I'm using the exact same parameters to update my hidden state. So I take the word embedding for students, multiplied by this matrix W sub E. I take the previous hidden state, H sub 1, multiplied by W sub H, and then I apply the nonlinearity, and I get this new hidden vector, this red vector here, right? So unlike the concatenation fixed window model, which, as I mentioned, is not sharing weights among the different positions, here you can see I'm using the exact same W sub H and W sub E for every single position in this prefix. And I can just step forward left to right to integrate the word opened into this hidden representation, integrate the word there into this hidden representation. And now I've finally modeled my full prefix. So I can apply the softmax layer over the final hidden representation of this recurrent neural network and then predict the next word. So this approach has a lot of advantages because I can apply this to arbitrarily long prefixes, right? It doesn't matter if it's 2 words long or 500 words long. I just need to do more steps in order to model the 500 word prefix, right? But I'm sharing these weights, so the number of parameters in this model does not scale with the number of time steps or the length of the prefix. I just have these 2 weight matrices here, W sub H, W sub E, that are used for all of the computations. So the advantages of this model are, of course, it can process variable length inputs. Compute does not depend on the number of time steps. The weights are shared. There are disadvantages, though. The main one is that this is a very slow process, especially for longer sequences, because I can only compute the representation of the 4th time step after I've computed the representation at the 3rd time step. So there's this dependency on the time, the position, which I don't have in the concatenation model, right? In that model, I can just compute the final prefix representation in one shot. Here, I have to do it in 4 steps, so it's slower. And also, it's very nice in theory that this model can handle arbitrarily long input prefixes, but in practice, this is not the case. So the model will routinely forget information that it's seen in the distant past and focus more on more recent words. This is not a solved problem. In the model that we'll talk about next week, the transformer, suffers from this problem as well, but to a lesser extent. All right, so any questions about this recurrent neural network? Yes? Oh, this is actually a very good question. So the question is, why is not remembering the distant past a disadvantage? Because when we're doing this task of predicting the next word, intuitively, the more recent words, the words that have just occurred, are going to be way more useful for computing the prediction of the next word, right? That said, as you get more and more distant into the past, there are still important bits of information there. They're just more abstract that could help you predict the next word. So for example, if you're predicting the next word in a story, right? You might want to know all the key events that have happened in that story or some background about the characters, things like that, which if the model forgets, it might hurt its prediction of the next word. But you make a good point because it's very hard to tell when that information is needed and what kind of information is needed from the distant context. That we'll have a whole lecture on much later in the semester.
Since we're just adding up the nonlinearities after each step,
Mm-hmm.
how does it encode like the temporal nature of data? It's like in the end, it's just one big addition.
It is, but it cannot just be decomposed into a giant addition, right? It has to occur step by step, and at each step, you are merging information about the current word with all of the words that you've seen previously. So there is this kind of order property that is preserved in this kind of model. There's improved versions of their current network, like the LSTM that you might have heard of. These have improved capabilities of, for example, if I observe the word the, maybe I shouldn't update my hidden state too much because this word doesn't contain that much semantic meaning. Versus if I see the word students, like this is a huge important meaning containing word that will be useful in predicting the next word, so I might want to make a very drastic update of my hidden state. So yeah, the order information is there. There are many experiments that show that these kinds of recurrent models encode the position information of words. You have a question?
Yeah, just the determination of the W sub H and W sub E matrix. That's what occurs during the training stage of the model, right?
Yes, that's correct. So W sub H and W sub E are learned parameters of this model. They start out as being initially randomly initialized, and then they are updated through training, just like the word embeddings and the softmax matrix that we saw earlier in this class.
So that's why now they're sort of static and like pre-calculated.
Yeah, now this is just, we haven't even shown what the values are, right? But next class, we'll talk about how to update these. Any other questions? Yeah.
Usually we don't update the hidden state directly during training. Whatever the initial hidden state is it always randomly initialized?
Yeah, that's a good question. So these hidden states are not parameters of our model, right? They are the outputs, the intermediate outputs of these computations between the weight parameters of the models, these weight matrices and the word embeddings. That said, the initial hidden state is different, right? This is something that we start with for every prefix before we observe any words. It's common to either randomly initialize this and learn it, or just set it to a fixed value. Like you could just set it to all zeros, for example, which is also common in some libraries. So it depends how you want to handle this, but you can treat it as a parameter or a constant.
Is there a usual number of layers for these, or does it depend on the situation?
Yeah, so the number of layers in a recurrent neural network is, again, a hyperparameter, so it depends on the things we talked about with the size of data, amount of compute you have, and so on. Yeah. You have a question?
Yeah, I was going to ask, like, why are we transforming between the different WHs?
Yeah, so the question is, well, essentially, why do we have this WH matrix? Because the previous the previous H is already of the correct dimensionality, so why do we need this projection? You don't need the projection. It's a good way of adding more parameters to your model, so that it just allows you to learn more complicated functions, and that's why you also have depth, right? You can stack many recurrent layers on top of each other. Just improves the expressivity of the model overall. Other questions? All right, so in the next class, we will focus on backpropagation, or how to actually adjust these parameters, and then we'll talk about the building blocks of the transformer and move from there. So see you then. Also remember the talks tomorrow. If you want extra credit, please think about attending the talk in person at 4.
Thank you.
Yeah.